So now that we've looked at some of the rules for oxidation numbers, let's go ahead and practice assigning oxidation numbers. And here I have, oh, whoops, giving them away. Here I have several different compounds with nitrogen in it. So let's go ahead and determine the oxidation number on a single nitrogen atom or ion in these compounds. So if we look at this first one here, we have nitrogen in its elemental form, and so we know that the nitrogen in that species is 0. So all the oxidation numbers are 0. Looking at this next compound, it's an ionic compound, right? So for ionic compounds, the overall charge has to be 0, and the charge on the ions themselves is the oxidation number. So if each of these sodiums is contributing +1, and there are 3 of them, that means to balance all 3 of the sodiums, the nitrogen has to be a 3 minus. All right, yes, 3 minus. Now, this one we go to the rules for fluorine. Fluorine has a -1 charge, or a 1 minus charge here. There are 3 fluorines, and so that means that the nitrogen has to have a +3 or a 3 plus charge on it. 3 plus charge in order to balance all 3 of the -1 charges there. For this compound, oxygen generally has a 2 minus charge, but there are 3 of them, so 2 minus times 3 would be overall -6. I'm going to actually write it like this, -6, but this nitrogen has to balance it out. So -6 plus X is equal to -1. That's the charge on the species. If we solve this simple algebra problem, we see that X has to be a +5. So +5 there. Next we go to this compound. Again, 2 minus is the oxygen state. So if oxygen is 2 minus, and there's one of them here, we have -2 plus 2x equals 0. In this case, our x has got to be +1. So +1 times 2 is 2. -2 is 0. Alright, so this one is pretty simple. Oxygen is -2, which means that nitrogen has got to be +2. And in this one, we can set up another algebra problem. So we got 2x, or -2x times 2. Okay, oh, hold on. Let me actually write it as -2 times 2 plus x is equal to -1. Solve this one, so it's -4 plus x equals -1. So x is equal to +3. So nitrogen is +3. So you can do these algebra problems if you can see it. You don't have to set up the algebra problems, but I was just showing you how you can do that even if you can't see if they should be +1 or +2. You can use a little bit of algebra to figure it out. All right. So if the compound is a little bit more mm, complex, say you have an ionic compound with a polyatomic ion, the best thing to do is break it into its individual ionic pieces. Okay? So you have a 2 plus ion and an SO3 2 minus ion. So this oxidation state is obviously 2 plus. This oxidation state, well, we have 2 different element types. We have oxygen, which will have a 2 minus charge, and then each one of those is contributing 2 minus. And so we have to do 3 times 2 minus is -6, and then we have plus x equals -2. Well, in this case, if we solve this one, x has got to be +4, so that is the oxidation number on sulfur. So bringing this in, +2, +2, +4, -2. One last thing you got to know that's important is being able to recognize what happens when you throw a metal into an acid. So the 2 things that you get if the reaction occurs. So if a reaction occurs with a metal and an acid, you'll end up getting the salt of that metal, so a metal with the anion for the acid coming and combining with the metal as a cation, so there's going to be a transfer of electrons from the metal to the hydrogen, and we're going to get hydrogen gas. So hydrogen gas is a very common product when you're doing this sort of reaction. And notice the oxidation states of these species here. We're going from magnesium 0 and hydrogen +1 to magnesium 2 plus and hydrogen 0. So that is how we are able to visualize where all the electrons are going. Got 2 electrons from the magnesium going to each of the hydrogens, and then the 2 hydrogens then become hydrogens with 1 electron. They end up forming a covalent bond, and the magnesium stays as a 2 plus charge. Well, in solution, we say it's magnesium chloride, but remember, in reality, magnesium and chlorides are dissociated in solution, and so we just call it magnesium chloride, and then we have this aqueous for the charge state, or for the state of the matter.